Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin. At each point along a smooth space curve. All right, so we have a curve. All right. The osculating plane is the plane containing the point, the direction of motion, and the direction of acceleration at that point. It's more or less telling us what the osculating plane is. It's essentially saying, let's find the plane that captures the important pieces of information about what's happening with that curve. So, find the osculating plane at time t equals 0 for, oh my gosh, there's a lot of stuff here. R of t cosine 2t minus 4t plus 2, e to the 3t plus 1 minus 2t squared, 2 sine of t plus 3 plus e to the t. All right, well, we know what? We know it contains the point. That's going to be r is 0. We know it contains the direction from velocity, so it has r prime is 0 as a vector in the plane. Direction from acceleration, so it has r double prime is 0 as a vector in the plane. So we're going to need the first and second derivatives. So that's probably a good place for us to start. All right, so we have r prime. Let me get a darker color here. All right, here we go. Yes, r prime. Yeah, that's nice. So the thing is, these are the same things we did in Calc 1. We're just going to do it 3 times, 1 for each slot. So we have derivative of cosine, negative sine, don't forget the chain rule, so minus 2 sine 2t, derivative of negative 4t, minus 4, derivative of 2 is 0. Derivative of e to the 3t, we're into our second slot, by the way, 3e to the 3t, derivative of plus 1, 0. Minus 2t squared, minus 4t. Derivative of 2 sine t, 2 cosine t. Derivative of 3 is 0, and then derivative of e to the t is e to the t. And go ahead, we'll do r double prime. Okay, so again, derivative of sine is cosine. And don't forget, another factor of 2. So we're going to have minus 4 cosine 2t. Derivative of negative 4 goes away. Comma. Then we have derivative of 3e to the 3t. Another 3 comes down, multiplying, giving us 9e to the 3t. Derivative of minus 4t, minus 4. Derivative of cosine, negative sine, so minus 2 sine t. And then plus e to the t. All right, good. Good. So we have our derivatives in place. Next up, let's evaluate. Okay, so we're going to need to evaluate everything. So we have r of 0. Well, cosine of 0, 1. 4 times 0, 0. And then add 2. E to the 0 is 1. Add 1. 2t squared is 0. Sine of 0 is 0. Plus 3. E to the 0 is 1. All right, so that's giving us the point 3, 2, 4. And that truly is a point. R prime of 0. Okay, plug it in. Sine of 0, 0. Minus 4. Then we have 3 e to the 0, which is 3, minus 0. All right. Cosine of 0 is 1, so then we have 2. And e to the 0 is 1. All right, so that gives us the vector minus 4, 3, 3. Right? Minus 4, 3, 3. Okay, and r double prime is 0. All right, well, what will that be? Well, we have minus 4 times cosine of 0, which is minus 4. 9e to 0, which is 9. Subtract 4. And Sine of 0 is 0, so that's 0. And plus e to 0 is 1. Okay, so that gives us minus 4. 9 minus 4 is 5. And 0 plus 1 is 1. Okay, so in terms of where we're going, here's our point. And now these are vectors in our plane. All right, so we now have the information we need to make the plane. So we've done the calculus part, so we can sort of ignore where this came from and say, you have a point, and I know it really looks a lot like a vector, but it's a vector representing a point. We have a point, you have two vectors in the plane. So what do? Well, we need our normal, and if we have two vectors in the plane, well then we have a way to make a normal. We're going to cross them, right? We're going to take their cross product, and that will give us something which is perpendicular to both of them. All right, so let's do that. So here we go. I, j, k. It doesn't matter which order you put them in, but put them both in. Minus 4, 3, 3. Minus 4, 5, 1. Okay, so do our diagonals. I times 3 times 1, 3i. J times 3 times minus 4, minus 12j. K times minus 4 times 5, minus 20k. Other diagonals. Minus 4 times 3 times k, minus 12k. But remember, you have to subtract that value. Okay, so we're subtracting negative 12k. 5 times 3 times I, 15i, but we subtract that. So minus 15i. 1 times minus 4 times j, that's minus 4j, but we are subtracting minus 4j. All right, so we have 3 minus 15, which gives negative 12. Minus 12 minus minus 4, that's really minus 12 plus 4, which would be negative 8. Minus 20 minus minus 12, that's minus 20 plus 12, which would give us negative 8 again. Now, here's the thing. When it comes to normal, and this is our goal, we're making our normal, we only care about direction. And so the punchline here is we can scale. Now, scaling says you can introduce a number. The same thing lets you pull out. So if you ever see common factors, pull out the common factor and give yourself easier things to work with, which is to say, hey, you know what we could do? Let's pull out a negative 4. Why not? Let's see if that would work. So if we pull out negative 4, we'd be left with what? Well, 3, 2, 2. So we can use this as our normal. Now, is this going to work? Because whenever you do computations like computing the normal, it's easy to do a small mistake. Just like one mistake can derail us. But the nice thing is there's also ways for us to check. There's easy checks. And what's the check? Well, you do the dot products. So here we go. We're checking perpendicular. Minus 12 plus 6 plus 6. 0. That's good. And then just for extra caution, minus 12 plus 10 plus 2. 0. Nice! So now we know for sure this is the vector that we want. Okay, so that's going to work. So we have our point, we have our normal. Now, we know that these numbers are our coefficients. So we have 3x plus 2y plus 2z equals something. It's the age-old question. What's in the box? What's in the box? Right? What goes there? Well, so these numbers are our coefficients. Now, to figure out what goes here, that's where the point comes into play. So we're going to take the point. X is 3, y is 2, and z is 4. Okay, so what do we have? We have 9 plus 4 plus 8. All right, well, let's see. 9 plus 4 plus 8. Well, 4 plus 8 is 12, a dozen, and add 9 would make it 21. So that's what goes in the box. So our final answer, what's our osculating plane? 3x plus 2y plus 2z equals 21. And there we go. Ah, that wasn't bad. That's a nice plane. Good for you. Good for us. Woohoo! A particle is moving through space, and we have the acceleration. 4e to the 2t plus 4, 6 sine t plus 12t, 6, and that's at time t. At time 0, we have that the particle is at an initial point, and it has an initial velocity. The question is, what's the position of the particle at time t equals 2? So we have acceleration, and acceleration, how does it connect to position? Well, acceleration is the second derivative of position, right? You start with position, one derivative gives you velocity, two derivatives gives you acceleration. So we got to sort of work our way back up. So it's like, okay, so we basically have to integrate twice. Now, every time we integrate, we have constants that we need to solve for. Constants plural, because we have multiple slots. Each slot will get its own constant. But that's okay, because we have some initial conditions, and that will help us solve for our constants. So let's write down what we have. Okay, we'll start with our a of t. And here we go. 4e to the 2t plus 4, 6 sine of t plus 12t, and 6. Again, this is like a Calc 1 problem. We just have to do it 3 times, one for each slot. So let's go. Integrate once. So now we're going to integrate, and we're going to get velocity. All right, so integrate term by term. Here, integral of e to the 2t would be e to the 2t, but remember to account for the 2 on the inside, so we need to divide by 2. So that would be 2e to the 2t, and then we have a 4, which becomes 4t, plus a constant. Integral of sine, negative cosine. Oh, that's a pesky one. It's an easy place for people to lose a minus sign. So be careful with your sines and cosines. Integral of 12t, well, integral of t would be t squared divided by 2. So you have a 12, so that becomes a 6 t squared, and don't forget your constant. And then the integral of 6, 6t, and don't forget your constant. Okay, so that's our velocity. And we're told it has an initial velocity. So in other words, we have some initial conditions. V of 0 is this value 1, negative 2, 4. That's from our initial conditions. But it's also plug 0 into here. Well, e to the 0 is 1, so that would be 2 plus 0 plus c, comma. Cosine of 0 is 1, so that's minus 6 plus 0 plus d. And then 6 times 0 is 0 plus e. Okay, so let's see, what does that give us? 2 plus c equals 1. Okay, and we'll come to that in a second. And d, or minus 6 plus d equals minus 2. And e equals 4. Oh, I can solve for e. That's pretty easy. And actually, notice there's not like, oh, e, c, and d are all like mixing up together. They don't. And so these are all very simple and straightforward. They fall immediately from the initial conditions. You just have to figure it out. So it says, okay, so c has to be minus 1. Add 6 to both sides. D has to be 4. And e is also 4. All right, so updating. Where our velocity is what? Well, 2e to the 2t plus 4t minus 1, comma, minus 6 cosine t plus 6t squared plus 4, comma, 6t plus 4. All right, good. So we integrated once, and we used our initial conditions. Now we'll do it again, right? It's the problem's so nice, we do it twice. All right, so up to position, where we use r of t. So we're going to integrate term by term. Integral of 2e to the 2t, well again, we're going to have e to the 2t, we're going to divide by 2, so we actually just end up with e to the 2t. Integral of 4t, well, we'd have a t squared divided by 2, so that's a 2t squared, and a minus t plus a constant. Notice I'm not using the same symbol. So I didn't do c, 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 because they're all different constants. So I'm working my way through the alphabet. Don't worry, it's a big alphabet. And we should be fine. And if we ran out of letters, we could start using different things, right? It's all just sort of placeholder saying something, something. Integral of cosine, positive sine. So we'll still have that negative, so negative 6 sine. And then the integral of t squared would be t cubed over 3. So we're going to divide, so that becomes 2t squared. Then we have plus 4t plus constant. Then the integral of 6t, well, that's going to be t squared over 2. There's already a 6, so that becomes 3t squared plus 4t and plus h. All right. That's a big function. Well, we have an initial point. Okay, so r of 0, that is at the point 3, 6, 1. Okay, that's what we have here. But that's also, okay, plug in. We have 1 plus 0 plus 0 plus f. All right, then here we have 0 plus 0 plus 0 plus g, because sine is 0, t is 0, t is 0. And then we have 0 plus 0 plus h. Okay, so what does that lead us to? Well, that tells us that 1 plus f has to be 3, g has to be 6, h has to be 1. Okay, so f is 2, g is 6, and h is 1. So our r of t is, well, we just write it down, e to the 2t plus 2t squared minus t plus f, so plus 2 minus 6 sine t plus 2t squared plus 4t plus g, so plus 6, 3t squared plus 4t plus h plus 1. Okay, now that's r of t. So we now have our position at any time. You give me a time, plug it in, we got a position. Woohoo! Nice! Nice! All right, so what do we plug in? 2. So here we go. R of 2. Well, that's e to the 4. 2 times 2 is 4. 2 times 2 squared. And let's see. Wait. Something seems... Are we good here? Yep. 2 times t2 squared. Sorry, I was double checking. Just want to make sure that it should be a t squared, not a t cubed. You know, it's good to doubt yourself a little bit. Enough so that you check. Not so much that you have negative feelings about yourself. No. Just a small amount of doubt is okay. All right, so 2 times 4 is 8, minus 2 plus 2, comma. And then we have negative 6 sine of 2. Not much you can do with that. And, okay, here we go. I knew that there was going to be something suspicious. Here's my error. Something felt off. 6t squared. Right, when you integrate, it was 2t cubed. Cubed. See? Easy problem to fix. Okay, so 2 times 2 cubed. Well, that's 2 times 8. That's 16. Okay, 2 times 4 is 8, and plus 6. All right, 3 times 4, 12, plus 8, plus 1. All right, well, we can just add the terms. E to the 4th, and 8 minus 2 plus 2 is plus 8. Then we have minus 6 sine of 2. And then 16 plus 8 is 24. Plus 6 makes 30, so plus 30. And then 12 plus 8 plus 1 is 21. And there we go. That's it. Now, you might say, do we represent this as a vector or as a point? And because you'll notice that the initial point is given in vector form, we should leave it in a vector form. And if they'd given us our initial point like as a point, we probably would say, oh, let's change it to a point, which would just be shoo, shoo. But this is like a fine detail, and I think we're amongst friends, right? Math is a friendly place. And so we're good to go. We're good to go. All right. Woohoo! Yay! Oh my gosh. And I know it feels like a lot, but if you just think about each slot, that's something we've done before. It's just a matter of doing it over and over and over again. And hopefully by this point, these are things that we can do really well. So we're going to do great. We're going to be wonderful. If a particle travels along a curve, and we have r of t is t sine 4 log ti plus t cosine 4 log tj minus 8tk from time t equals 1 to t equals 3, how far has the particle traveled? Okay, interesting. Well, now, so this is, how far has it traveled? Now, not where is it here, where is it there, what's the distance between them? But we're talking about distance of curve. So when we're after that, we say, okay, there's a way to find this. And our distance that we traveled is found by the following. Namely, it's the integral from a to b, magnitude r prime of t dt. Okay, so that's our underlying formula. So most of the work, in fact, the vast majority of this work is going to be saying, let's find the magnitude of r prime. Once you found that, the rest of it's usually very straightforward. Maybe a little bit of work in the integration, but usually when we ask these types of questions, the magnitude of r prime will turn out to be something wonderfully beautiful. And I hope that's true here. Well, only one way to find out. So let's start here. Now, they gave it to us in this form where we have these ij's, k's. That works great. I personally prefer component form. It's a little bit easier for me to keep track of things. And so I can convert to the component form. I'm just going to put everything inside its slot. So t sine 4 log t and comma t cosine 4 log t comma negative 8t. So step 1, r prime. Because if we're going to find the magnitude of r prime, we kind of need to know r prime. So product rule, derivative of the first, sine 4 log t, and so derivative of the first times the second, so that's 1 times the sine 4 log t plus the first times the derivative of the second. Now the derivative of sine, chain rule here, cosine 4 log t, then times by the derivative of the inside, and derivative of 4 log t would be 4 over t, right? Comma. Okay, same thing, product rule. Derivative of the first is 1 times your cosine plus the first times the derivative of the second, derivative of cosine, negative sine, and so chain rule again. So negative sine, inside remains the same, times by the derivative of the inside, and finally, derivative of minus 8t minus 8. Okay, now, this may not be looking good, but let's have faith. Let's have faith. And, well, there's a couple of things that are nice. The t's cancel, so that's good. So, okay, that's a little bit of promise. Maybe that's why they put the logs in the inside. And, okay, we can rewrite it really quickly. This is not much, but just so we can make it clear, in our next step we have 4 cosine 4 log t, comma, cosine 4 log t, subtract 4 sine 4 log t, and negative 8. All right, now we're going to find the magnitude. Now when it comes to finding magnitudes, when we see sines and cosines, there tends to be two things that happen. One is you get sine squareds plus cosine squareds, which become 1s, which are like, yeah! And it doesn't matter what the inside looks like. As long as it's sine squared plus cosine squared where the insides match, life is good. So it could be as simple as sine squared x plus cosine squared x, or something like sine squared 4 log t plus cosine squared 4 log t. It's all 1. Now the other thing that tends to happen is that you get cross terms, but you'll notice how one of these is a plus and one of these is a minus. We're kind of fingers crossed, hoping for cancellation. And all right, well, let's do it and see if we have it in that case. So magnitude of r prime. Okay, so square root of, and sine 4 log t plus 4 cosine 4 log t squared plus cosine 4 log t minus 4 sine 4 log t squared plus negative 8 squared. Now we're not going to go into the integral until we have simplified as much as we can. As much as we can. Okay, so this is going to take space. We expand it. So this is like a plus b squared. So we have the first term squared, sine squared 4 log t. Then the cross terms. So that's a squared 2ab. So 2 times this times that. So there's, notice that 4 there. So 2 times 4 makes 8 sine 4 log t cosine 4 log t. B squared, that term squared, that makes 16 cosine squared of 4 log t. Okay, so that's the first term. Plus, okay, similar thing here, cosine squared 4 log t, cross terms. So because of the minus, it'll be a minus 8 cosine 4 log t sine 4 log t plus 16 sine squared 4 log t plus 64. Okay. Oh, we barely fit it on the page, but we did fit. All right, now remember we said some things should be happening, and we see that. See, there's a sine squared here, matches with this cosine squared there. That's nice. There's this 16 cosine squared, which matches with this 16 sine squared. Also nice. So those will come together. And, not to be outdone, we also have the cross terms, 8 sine cosine minus 8 cosine sine. Now those cancel out. So what do we have? Well, we have from this sine squared plus that cosine squared, that becomes 1. Okay, so we have square root of 1. These terms are gone. This 16 cosine squared and that 16 sine squared becomes 16. And then that 64 becomes 64. All right, 1 plus 16 plus 64, that's 81. And that's 9. Okay, so this is, there's a term for this. We call this nice, which is to say it really simplifies to something quite beautiful, very beautiful. So now we're ready to tackle. We've done the hard work. This is the hard part, but we're not out of the woods yet, right? So we say we have to put into our formula. So we're going A to B, 1 to 3 of 9, that's the magnitude, dt. Well, it turns out that's an integral we can do. That's 9t from 1 to 3, which is 27, 9 times 3. Subtract 9 times 1, giving us our final answer of 18. So the particle has traveled 18 units along this curve. And there we go. Wow. You know, at some point here, we're probably like getting nervous. Like, oh my gosh, are we going to be able to do it? And sometimes the expressions that look particularly terrible simplify a lot. And on the other hand, some things that look particularly simple become really, really annoying. So I guess the moral is we don't judge a problem by its cover. We just let the problem flow through us and just say, let's find out what's going. And have some belief. Have some belief that the problem likes us and that the problem writers like us. All right. Good. Good. An object's acceleration vector at time t is given by acceleration is 0, 0, g, where g represents a constant. We can think of g as gravity. All right, at time 0, its position vector is 0, 0, 160, and its velocity vector is 12, 12, 0. If at some later time, the object's position vector is 36, 36, 16, find the value of g. And, all right, I noticed that for some reason there's an extra comma here. Don't worry, that's just a typo. Okay, so what can we do? Well, we have acceleration, so we can find position and we can find velocity. Now there'll be this extra factor of g. That's okay. So let's go ahead and figure out, because we have some information about position later on. So we start. Acceleration, that's our 0, 0, g. So velocity, well, that's going to be some constant c, some constant d, and then g times t plus some constant. But we have our velocity vector at time 0. So we can say, oh, well, wait a second, v of 0, that's equal to 12, 12, 0. And if we plug in t equals 0 into this expression, we get c, d, e. Well, that tells us c is 12, d is 12, e is 0. So we say, so our velocity then, using this information, becomes 12, 12, and g times t. Okay, so we started with acceleration, integrated once, we got velocity. Used our initial conditions to solve for the constants that came in. Well, let's do this again. The idea is so nice, we'll do it twice. So starting with our velocity, after we found our constants, we get 12t plus some constant, f. 12t plus some constant. And so I don't want to confuse it with little g. I'll go ahead and skip that, h. And then integral of g times t is a half gt squared plus some constant. And I'll go ahead and jump to k. Why not? I can do whatever I want. All right. Cool. Well, again, we have an initial position. So, r of 0 is what? Well, we plug it in. F, h, k. And that has to match 36, 36. Oops. I was looking there. I have to look there. That has to match 0, 0, 160. Yes. Make sure you're looking at the right part. Okay. So that says what? F is 0. H is 0. K is 160. Okay. So that says we really have what? Well, it says we have 12t, 12t, and then 1/2 gt squared plus 160. Okay, all right. Well, we're almost there, almost there. So what is the last thing? We now say, look, at some later time, it doesn't tell us when, but at some later time, we have its location. So we know that at some point, 36, 36, 16 has to match 12t, 12t, 1/2 gt squared plus 160. Well, we just start matching the entries. So the first entry and the second entry, they're basically the same. It says, hey, you know what? This 36 has to match with the 12t. That says that the later time was 3. So this is our later time. And in a similar way, hey, this has to match with that. So we get that at time t equals 3, 16, and y3, because that's our later time, is equal to 1/2 times g times 3 squared. So that's actually, we'll put that as 9/2 g plus 160. Well, we can move things around. We can subtract the 16, we can move this around, and so minus 9/2 g, 160 subtract 16 is a number, 144. Okay, good. I'll trust you. All right, 144. So then g, well, that's minus 2/9, right? So just flip it over, move it across, times 144. Well, turns out if you take 9 and divide it into 144, you get 16. Now, if you're not sure about that, you can really think of 144 as kind of gross. Okay, no, actually, sorry. 144 is a dozen times a dozen. And so a dozen is called the gross. And so it's 12 times 12, or 3 times 3 times 4 times 4. So what you end up with is 4 times 4, because the 9 and the 3 times 3 is canceled. That's how you get 16. Don't forget there's a minus 2 there, and so you end up with negative 32. All right, and there we go. Now, they didn't give us any units, so we're not expected to put units in, but that negative 32, highly suspicious, because it turns out negative 32, if you measure in feet and seconds, that's the gravity that you experience on Earth. Wow. That, I guess it really brings it down to earth, this problem. Okay. All right. Well, good. The position of a particle moving in three-dimensional space at time t greater than or equal to 0 is given by this expression, t minus t cubed over 3, t plus t cubed over 3, and t squared. Find a time, capital T greater than 0, such that the particle travels 12 root 2 units from time t equals 0 to t equals t. So we aren't asking for, what's the distance that we traveled between 2 times. Rather, we're saying, hey, here's the distance we traveled. What were the times? And I'll tell you that the start time was 0. Now, in some sense, this gives us a little bit of hope, because it says, well, you got to have something nice enough that you can actually solve it, which means that we have to probably have a pretty nice answer. Okay, so whenever we're dealing with how a particle travels, we always say the most important thing, and the thing we need to invest the most in, is we want to figure out magnitude of r prime of t. So that's our goal, because we have integral a to b magnitude of r prime of t. And this is the hard part. Now, so that's where we're going to put our energy. Okay, so let's think about this. So we have r of t. Let's go ahead and do r prime of t. We have some space here. So that would be 1 minus, and then derivative of t cubed over 3. 3 comes down, so that actually cancels off nicely. T squared. And here we have 1 plus t squared, and here we have 2t. All right. So, what do we get? Well, the magnitude of r prime, okay, so that's going to be the square root of, we have 1 minus t squared squared plus 1 plus t squared squared plus 2t squared. Okay. And this is going to become the square root of, we'll get 1 minus 2t squared, then plus 2t squared, sorry, plus 1t squared, excuse me, t squared squared t to the fourth, plus 1 plus 2t squared, and then plus t to the fourth plus 4t squared. All right, cool. Cancel, cancel. So what are we at? We are at square root of, well, we have a t to the fourth here, and yeah, this is what happens when you don't pay attention. So t to the fourth and a t to the fourth, that's 2t to the fourth. We have a 4t squared. All right, 4t squared. 1 and 1 makes 2. Well, hey, we can factor a 2 out of that. So if we do, that's 2 times t to the fourth plus 2t squared plus 1. And that's a perfect square. And we kind of suspect magnitude of r prime should be nice. And so we're sort of on the lookout for perfect squares. So that's t squared plus 1 squared, which becomes square root of 2 times t squared plus 1. All right, cool, nice. Okay, so that's good. So what can we say? Well, we can now rephrase this problem. And so this problem can be written in the following way. Namely, we know the distance we've traveled is 12 root 2. So our goal is find a capital T so that 12 times root 2 is equal to the integral 0 to capital T of the magnitude of r prime. So that's square root of 2 times t squared plus 1 dt. Okay, so that integral, well, it's the square root of 2, the square root of 2. You get 1/3 t cubed plus t. Evaluate from 0 to capital T. So, square root of 2 times 1/3 t cubed capital T plus capital T. And you plug in 0, you get 0. All right. Well, notice they both have a root 2, so we need that 12 is equal to 1/3 capital T cubed plus t. Now, in this case, you might say, is there any hope? Can we do anything? And sometimes we can solve for it, but you know, there's another strategy that can work, which is you can say, and this is a wonderful strategy in maths. It's called guess. Can you guess it? And if you can't guess it, you use better tools, but if you can guess in reason, you can say, well, let me try something. So I'm looking at this, and I'm thinking, well, this is a whole number, and they're probably going to give us a nice number, because, you know, mathematicians are nice. It's in their nature. So I'm looking for a nice number, and when I plug in, I get a whole number. And I see this 1/3. So I say, well, my goodness, I somehow have to get rid of that 1/3. So I should have something which is a multiple of 3. It can't be a huge multiple of 3, otherwise it's going to be big. The smallest multiple of 3 is 0. Okay, that doesn't work. The next multiple of 3 is 3 itself. So let's guess. So does t equal 3 work? Well, we have 1/3 times 3 cubed plus 3. Well, that's 27 over 9. 27 over 3 is 9. That's 9 plus 3. And that does equal 12. So we're like, yes, we found it. And so once you find it, it has to be the answer. And so we're done. T equals 3. Now, I know that's somewhat unsatisfying. However, it's something where there's a cubic involved. And so if there's a cubic involved, it's got to be something that we can guess, or it's going to be super easy. And the other thing you could do is, of course, say, oh, it's a cubic. Think of rational solutions, and then go through your list. But we can also say, hey, people are reasonable. Let's try a good guess, and let's see what happens. And so there we go. And yeah, we're done. Woohoo! All right. Consider the path given by r of t, e to the t, 2 sine 2t plus cosine 2t, e to the t sine 2t minus 2 cosine 2t, and 12e to the t. We're asked, find the tangential component of acceleration, this a sub t of t, along this path. Okay, now, how do we find the tangential component of acceleration? There's a couple ways to do it, but in general, the easiest thing to do is the following. Namely, say, look, a sub t, that's the derivative of the magnitude of r prime. Okay, so if we're after a sub t of t, that's our goal. Find that magnitude of r prime. Fingers crossed, it's something easy. And then once we have that, life is good. So all of our work is going to be doing this, finding that magnitude of r prime. Once we do the derivative, if we do our job right, and they ask the question right, everything else will be pretty straightforward. All right, so let's start. We need to do r prime. And okay, well, just be patient and work it out. So r prime, I think we'll need some space. We have product rule, so take the derivative of the first, e to the t, times the second, 2 sine 2t, plus cosine 2t, plus the first, e to the t, times the derivative of the second. Derivative of sine is cosine. Don't forget the factor of 2. So that's 4 cosine 2t. Derivative of cosine, negative sine. And don't forget the 2 from the chain rule. So minus 2 sine 2t. All right, that's our first entry. Comma. Derivative of the first, e to the t, times the second, sine 2t minus 2 cosine 2t. And then plus the first times the derivative of the second. All right, so derivative of sine 2t, that's 2 cosine 2t. And then derivative of cosine is minus sine. So there's already minus. And don't forget they need a factor of 2. So that makes plus 4 sine of 2t. And then finally, derivative of 12e to the t is 12e to the t. Whew. We fit it in. All right. Whew. Now, at this point, you're probably like, ah, but remember, they like us, right? I'm pretty sure they do, which means something nice should happen. Well, notice here we have a 2 sine of 2t and a minus 2 sine of 2t. Those will end up canceling. Here we have a minus 2 cosine 2t and a plus 2 cosine 2t. Those will end up canceling too. And then on the other hand, these terms don't cancel, but they do combine in their respective slots. So what do we have? Cosine 2t, 4 cosine 2t, and e to the t. So that all combines as 5 e to the t cosine 2t. Similar, e to the t sine 2t, e to the t times 4 sine 2t times, all right. And so that makes 5 e to the t sine of 2t. And then that 12 e to the t. All right, good, good. Now, that's about as simple as we can get in terms of r prime. We need the magnitude of r prime. So, magnitude of r prime, well, square root of square the first term and plus square the second term plus square the last term. All right, well, what's that going to give us? Well, we get 25 e to the 2t cosine squared 2t. Then here we get 25 e to the 2t sine squared of 2t. And then here we get 144 e to the 2t. Whew! Now, what do we see? Well, everything has an e to the 2t. Okay, that's nice to see. And that's still inside of our square root. Notice here, cosine squared and sine squared. So, which is to say, hey, cosine squared plus sine squared equals 1. So, those first two terms, 25 e to the 2t, and then we have plus 144 e to the 2t. 25 plus 144, that gives us 169 e to the 2t. Well, is 169 a nice number? It turns out it is. 169 is 13 squared. So we end up with 13 e to the t. All right, now remember, that's not our answer. That's the magnitude of r prime. What do we need to do? Now we need to take the derivative. So our answer isn't going to be this 13e to the t. It's the derivative of 13e to the t. And the derivative of 13e to the t is 13e to the t. And that's our answer. Good, good. Not that, right? So don't forget, yes, in this case it turned out that, oh, the magnitude of r prime is the same as the derivative, but that's just because of that e to the t. If it had been anything else, you'd actually have something different. So don't forget, after you find the magnitude of r prime, you still need to take that derivative. And all right, great, we got it, woohoo! Consider the curve. R of t is 1 minus 3t plus 3 halves t squared I plus 4t to 3 halves j. And time is greater than or equal to 0. All right, well, that's probably reasonable since we have something to a 3 halves power, and we don't want to have a negative number to a 3 halves power. Find the point P that lies at a distance of 72 units along this curve from the point 1, 0 in the direction of increasing t. All right, now there's a couple of things that we can spot. Right away, we see it's a two-dimensional problem because 2 points, right, 2 coordinates. And you might notice something else. So this is our position, and if you plug in t equals 0, well, you get 1i, 0j. So this really says, oh, this is t equals 0. So what do we want? Well, we want to move a distance of 72 units, and we want to start at 1, 0. Where are we? So we have to find a point. Well, instead of focusing on finding the point, let's find the time. So an intermediate step says, at what time t, we'll call it capital T, have we traveled 72? So 72 equals the integral 0 to capital T, and why 0? Because that's where we start our point of magnitude r prime of t dt. All right, so that's our goal. That's our goal. Okay, so yeah, now that we know our goal, we say, well, let's do our classic thing, magnitude of r prime. And so, okay, we can either go to component form or work with it as is. And we don't have to go to component form. Maybe this time I'll do it without component form. Why not? You know, live life dangerously. So let's start with r prime of t. So r prime of t, take the derivative in front of each piece. So here, derivative of 1 is 0. Then we have minus 3. And then derivative of 3/2 t squared is plus 3t. That's I. Plus, here the 3/2 comes down. 4 times 3/2 is 6. So we're going to have 6 t to the 1/2 j. Now, the real important thing, the magnitude of r prime. All right, so that's the square root of. And now, when you have it in this format, whatever's in front of your terms gets squared and added. So minus 3 plus 3t squared, 6t to the 1/2 squared. All right, so that's the square root of. We start expanding. Let's see, what do we have here? We'll have 9, then the cross terms, minus 18t plus 9t squared. And that's the first part. Plus, here we'll get 36t. Well, okay, you can see that 36t and minus 18t, well, that can be rewritten as 9 plus 18t plus 9t squared. And you're like, oh, well, that's very convenient, because that's really the same as 9 times, and if you reverse the order, t squared plus 2t plus 1. Or 3, the square root of 9 is 3, and inside becomes t plus 1 squared. Now, technically, this would be 3 times the absolute value of t plus 1, but you see how t is greater than or equal to 0? So what does it become? Well, it says, hey, you know what? This is really just 3 times t plus 1. All right. So that's our magnitude of r prime. Okay. Good. Good. So far, so good? So we've done sort of a big chunk of the hard part. Now we've got to integrate it. So it's not that we're setting this to 72. That's not what we're doing. It's we're going to integrate. Okay, so this would say that we need 72 equals integral 0 to capital T of 3 times t plus 1 dt. Well, that's equal to 3 times 1/2 t squared plus t. Evaluate that from 0 to capital T. And that turns out when you plug in 0, you get 0, which is nice. So you get 3 times 1/2 capital T squared plus t. All right. Now we need to solve. Let's see, what can we do? Well, let's divide both sides by 3. So we need 24 equals 1/2 t squared plus t. And, okay, we can multiply both sides by 2. 48 equals t squared plus 2t. And, all right, so that's the same as t squared plus 2t minus 48 equals 0. And we can solve for t. Well, okay, what would we have? Well, we'd say we need two things that multiply to 48, negative 48, add to positive 2. Well, plus 8 and minus 6 have that. So that would seem to be it. So let's check. T squared minus 6t plus 8t is 2t and minus 48. All right, giving us two potential locations. T equals negative 8 and t equals 6. However, it's not two potential locations because one of them can't work. Remember, we said time has to be greater than or equal to 0 So we're not going backwards in time. Okay, so -8 is out. You're just out. All right, so we say, aha, it's going to happen at time t equals 6. So is that our answer? And why not? Okay, it's not our answer. And why not? Well, because that's the time it happens. What does the problem ask us to find? It doesn't say find the time, it says find the point. So our answer better be a point. Okay, fine. Well, how do we convert a time to a point? Well, we plug it in. You say, okay, so let's see. We can say our R of 6, well, we get 1 minus 18, 6 times 3, and then 36 divided by 2 is 18 times 3 makes 54. Okay, so that's the first slot. And then the second slot would be what? Well, it'd be 4 times 6 to the 3 halves. Now, what's 6 to the 3 halves? The answer is it's 6 to the 3 halves. It doesn't get clean. That's okay. Not all numbers have to be nice. But this is a vector. They gave it as a point, so we should write it as a point, not just clean it up. We'll write it as a point. If you take 54 and you subtract 18, you'd get 36. Add 1 gives you 37, comma, 4 times 6 to the 3 halves. And there's the point. That's where we will be once we've traveled a distance of 72 units along this curve. Cool. All right, good. So yeah, just keep track of things, right? Make sure you know what we have to have as our answer. Because sometimes it's easy to keep forgetting, like, wait, when do I stop? Because you should get to the answer and stop. Not stop before you get to the answer, not keep going after you get the answer. Get to the answer, stop. And all right, so I guess it's time for us to stop this problem. Find the components of acceleration, a sub t of t, and a sub n of t. So this is how much of acceleration is in the direction of motion, how much of acceleration is perpendicular to motion. And it's for a particle traveling according to the position function r of t, 3t squared minus 6t, 8t to the 3 halves, 3t squared plus 6t. All right. Well, what's the game plan? Well, the game plan, when you're trying to have a problem that says a sub t and a sub n, there's sort of a procedure. So let's sort of put out our game plan. So here's our plan. So first is we're going to find our r prime of t. And then, okay, once you did that, find magnitude r prime of t. Great. And okay, so you find r prime, find the magnitude of r prime. And now comes the fun part where we say, aha, we're ready to find one of our answers. And that's a sub t. That's the derivative of the magnitude of r prime of t. Okay, now we're not done. We have to find r double prime of t. And we have to find magnitude r double prime of t squared. Good news is it's the squared. And in particular, what we get is that we have magnitude r double prime squared is a sub t squared plus a sub n squared. Now you notice we have the term magnitude r double prime squared, and we have a sub t squared. Solve for a sub n. Okay, so there we go. And nothing is particularly bad. We just have to know our game plan and we follow it. Okay, and I will point out you can do the R prime and R double prime steps first and then just do the A sub t and A sub n back to back. All right, so good. The reason I write it this way, by the way, is just to say, oh, if you only need A sub t, then you can stop there. If you need A sub n, you go a little bit further. So with that in mind, we begin. So let's start. We have R prime. And that would be, we have 6t minus 6. The 3/2 power comes down, and that will leave us 8 times 3/2. That's 24 divided by 2. That's 12. T to the 1/2. Then we have 6t plus 6. All right. And, okay, magnitude of R prime. Okay, that's going to be the square root of 6t minus 6 squared plus 12t to the 1/2 squared plus 6t plus 6 squared. Okay. Well, 36t squared. Then we have our cross terms. So 6 and 6 and 2 minus 72t plus 36. And here plus 12 squared is 144. T to the 1/2 squared is t. And then similar on the other side, 36 t squared plus 72t plus 36. All right. Good. Now we combine, and what do we get? Well, we get 36 plus a 36 makes 72t squared minus 72t plus 144t plus 72t. Well, that makes a 144t. Plus 36 makes 72. I guess I didn't need that big of a square root. Okay, badly planned square root sign. Okay, that sometimes happens. So that's the square root, 72 times t squared plus 2t plus 1. Like, whoa, that's a square. Indeed, it is. That's going to be the square root of 72, and that'll be times t plus 1, right? Because this is t plus 1 quantity squared. By the way, 72 is 36 times 2. And so if we think about this, okay, so let's make some notes, because I'm writing stuff down. I don't want people to be skeptical. This is t plus 1 squared, 72, 36 times 2. So this becomes 6 square root of 2 times t plus 1. All right, now a skeptic might say, oh, wait, hey, don't you need an absolute value on that t plus 1? You know, you make a good point. However, I'm safe this time because we say, well, when does this even make sense? Like, when does this curve make sense? And if you look at this curve, you say, well, you see how you have that 3/2 power? It only makes sense if we're dealing with t, which are positive numbers. You can't take a negative number and take a square root of it. Not in this class. That's not how we roll. So, okay, so we're okay. We don't need to worry about the absolute value. Now, that's magnitude of R prime. Cool. Let's talk about R double prime. Okay, so R double prime of t. So take the derivative of the derivative. We get 6 t to the minus 1/2 and 6. Now, the good thing is we don't really need the magnitude of R double prime. We need the magnitude of R double prime squared. So magnitude of R double prime squared, well, that's going to be 36 plus, here it'll be 36 over t plus 36. Or if you like, that's 72 plus 36 over t. All right, our pieces are in place. We've actually done these parts here. So we're ready to more or less write down our answers. So let's start with our a sub t. A sub t is the derivative of 6 root 2 times t plus 1. And what does that turn out to be? Well, it turns out to be 6 root 2. All right, so a sub t is done. Now, we come to our a sub n. We say, oh, okay, well, for that, what do we have? We have magnitude of r double prime squared, 72 plus 36 over t is equal to a sub t squared. Okay, so square that number, that'd be 36 times 2, which is 72, plus a sub n squared. We see the 72's cancel. Nice. And now you take the square root of both sides. And I guess I should add a little note here. A sub n is going to be non-negative. So you're always like, oh, when I take a square root, is there a plus, minus? Plus, plus. And so we say, okay, so that says a sub n is the square root of 36, which is 6, over square root of t, which you can also write that as 6t to the minus 1/2. And that's it. We're done. Woohoo! Nice, nice. And so if you look at it, it's actually not a bad process if you have the plan. So have the plan. Know how to handle a sub t and a sub n. Find the curvature, kappa. So that, I know that looks a lot like a k. It's a kappa, Greek letter. That's one of the nice things about becoming a mathematician. You learn a little bit of Greek. And our curve is 4 cosine t, 3t, 4 sine t. And we're told, simplify your answer. Well, probably that means things will be simple. Okay, so let's quickly recap our plan. How do we find curvature? Now, when you're finding curvature in general, then the best plan is the following. Okay, so you're going to find r prime, and might as well, while you're at it, find r double prime. Okay, that's step 1. Step 2, find the magnitude of r prime and the magnitude of r double prime squared. And we'll explain why in a second here. So with this, you then find your a sub t. That's the derivative of the magnitude of r prime. And with your a sub t, you can find your a sub n. That's your magnitude of r double prime squared, which is a sub t squared plus a sub n squared. And you're like, okay, I see a suspicious lack of kappas in our plan here. And now is where the kappa comes in. So kappa, curvature, that is your a sub n divided by the magnitude of r prime squared. Okay, so there's our plan. All right, good, good. So we just have to follow our plan, right? Yes, yes. And you might say, is there an easy way to remember that? This is the easy way to remember it. And it's just one of those things where you just have to do it a few times. And there's nothing too surprising. And all right, so let's work through this. So we have our r. Let's do our r prime. So that'd be minus 4 sine t, comma 3 for cosine t. And we'll do r double prime while we're here. Minus 4 cosine t, 0, minus 4 sine t. Okay, so the magnitude of r prime, well, that's going to be the square root of, we have 16 sine squared plus 9 plus 16 cosine squared. Okay, well, sine squared and cosine squared combine. So they'll combine together to give us 16 plus 9. That's the square root of 25. That's 5. All right, how about the magnitude of r double prime squared? Well, no square root here. Minus 4 cosine t squared plus minus 4 sine t squared. Well, okay, that's 16 cosine squared plus 16 sine squared, which is 16. All right, now we've gone through and done the first two things. And usually when you get a curvature, these are going to be fairly straightforward to work with. Okay, so the next part is we start finding our a sub t and our a sub n. So a sub t, well, that's the derivative of our magnitude of r prime. Well, that's the derivative of 5, which is 0. So that says that acceleration never points in the direction of motion. Okay, that can happen. All right, great. So then we say, okay, magnitude of r double prime squared, which is 16, is equal to a sub t squared, okay, plus a sub n squared. But a sub t squared is 0 plus a sub n squared. So now say, well, what is a sub n? That says a sub n is 4. Okay, right? Because you take the square root. And now we have a sub n, and we have r prime, the magnitude of r prime. And so we put it all together, and what do we get? Well, we get that our curvature, kappa, is a sub n, 4, divided by magnitude of r prime squared, or 4 over 25. And that's it. We're done. Okay, so yeah, it's not so bad for this one. Well, it turns out this is a helix going through space, and so essentially it's almost like behaving like a circle. And circles have really nice curvature. And if you're not familiar with that idea, the history of curvature really is to say, hey, we love circles. It goes back to the Greeks. They loved two things. They loved lines and circles. And so everyone said, hey, we'll do what the Greeks do. And let's think of everything in terms of circles. And so the idea of curvature was, let's make things look like circles. And hence the idea. And since a helix does look a lot like a circle, it's not surprising that the curvature turns out to be a nice number that doesn't change. All right, good, good. Find curvature, kappa of t, for t greater than or equal to 0 for the curve, r of t, 1/3 t cubed, 4/5 t to the 5 halves, t squared. Simplify your answer. And lots of space. So who knows, maybe we'll need it, maybe not. Okay, so again, let's go through our procedure. When we're going for a curvature, there's a step-by-step thing that you need to know and you need to follow through on. So you start by saying, well, you better figure out r prime and r double prime because it relates to the curve, so it's not surprising that r prime and r double prime come into play. Say, all right, after you do that, figure out the magnitude of r prime and figure out the magnitude of r double prime squared. Good news is, this you don't have to worry too much about. The magnitude of r prime, you will put energy into that because you want that to be clean. All right, after you've done that, you've laid the groundwork. So you sort of go into phase 2. So let me switch colors for phase 2. Say, okay, time to work on a sub t and a sub n. So a sub t is the derivative of the magnitude of r prime. And then you have the magnitude of r double prime squared. Remember, this is acceleration. A sub t and a sub n are about acceleration, so that's not too surprising. A sub t squared plus a sub n squared. You're like, cool, but didn't you say something about finding kappa? Right, we did. And that's our last thing, is once we have all these pieces, we get to our final step, which is to solve for kappa. And kappa is, you take a sub n divided by magnitude of r prime squared. Okay, and we're done. So essentially, it's just one extra piece after doing your acceleration decomposition. So it's more or less finding a sub t and a sub n, and then just remembering one fact. Okay, so we have some work cut out for us. The good news is it doesn't look like too bad of a function, so we might make it up before midnight. Let's hope. All right, so we'll start. R prime. Well, derivative of 1/3 t cubed, the 3 comes down, that will make it a t squared. Here the 5/2 comes down, 4/5 times 5/2 will make it a 2, and it'll be t to the power 3/2. And then 2t. All right, derivative of t squared, 2t. While we're here, thinking derivatives, r double prime will be 2t. The 3/2 comes down. 2 times 3/2 is going to make 3t to the 1/2. And then a 2. All right, so that's our first dot. On to dot number 2. Okay, magnitude of r prime. Well, that's going to be the square root of, you square each term. So that'll be t squared squared. We'll go ahead and write that all out. T squared squared plus 2t to the 3/2 squared plus 2t squared, which is the square root t to the 4th plus 4t cubed plus 4t squared. Now, we can pull out a t squared, and then we're left with t squared plus 4t plus 4. And we're saying, oh, well, this is nice, because t squared plus 4t plus 4 isn't just anything, it's a nice thing. This is t plus 2 squared. And so now we're ready to take the square root. So we end up with what? Well, square root of t squared is, normally we say t, right? Well, normally we'd say absolute value of t. Normally we say t. Technically we should say absolute value of t. We are okay with just t. We don't need to worry about the absolute value because t is greater than or equal to 0. And then t times t plus 2. Or if you like, t squared plus 2t. All right, well, that's going to be good. That's actually going to be very convenient, I suspect. Okay, so that's t squared plus 2t. That's our magnitude of r prime. However, we're not quite out of the woods yet. Magnitude of r double prime squared. Okay, so magnitude r double prime squared. We don't need to worry about square roots on this one. We're going to take a 4t squared, so we're just squaring each term. And then 3t to the 1/2 squared makes it 9t, and then a plus a 4. All right, so next up, we are going to go and we are going to come to our next stage, stage 2. So what happens in stage 2? We're going to find our a sub t. Well, that's going to be the derivative of t squared plus 2t, right? Because it's the derivative of magnitude of r prime, and magnitude of r prime is t squared plus 2t. This is, to be honest with you, this is the hard part. This is where the problem writers spend all their time. It's like, oh, how can we make this crazy curve have a nice magnitude of r prime? And that's why you get weird functions here. You get weird functions here, so you get a nice thing there. And so don't stress too much about this not looking nice. You should stress if this is not looking nice. Well, but anyways, back to our problem. Derivative of t squared plus 2t is 2t plus 4. Cool. Now, we go right into this part. Say, oh, well, magnitude of r double prime squared, That's our 4t squared plus 9t plus 4 equals this. Whoops, why did I say 2t plus 4? 2t plus 2. My goodness. My goodness. All right, equals 2t plus 2 squared. That's our at squared plus an squared. Well, square that out. That's 4t squared plus 8t plus 4 plus an squared. All right, now we can move stuff across. The 4t squared are going to cancel. The 4's are going to cancel. There's a 9t, subtract 8t, leaves us with t. All right, now that's a sub n squared. So a sub n is square root of t. All right, so now we have a sub n. And the next step is to write down our answer. And so let's do it. So our kappa, a sub n, square root t, divide by magnitude of r prime squared. So we're going to have, well, we can do this part squared. So t squared, t plus 2 squared. And there we go. There we go. All right. So our curvature is root t over t squared times t plus 2 squared. The crowd's going wild. Woo! Oh my goodness. Oh my goodness. Well, it was a fun ride. I hope you hung in there. And so thank you so much. Thank you for all the work that you put in. I am so happy that you're putting the time and effort, because I know you're amazing. Let's keep going. Let's make it together, and let's have a great time.